eigenspace of beta H and F lambda, this impose conditions on all these spectral parameters. Or more physical way to think about it is that the momentum carried by all these excitations need to satisfy certain constraints or certain conditions. And this condition in question is the famous Besser-Einsatzs equation. So what do I do? So okay, I can show it in 10 minutes, 5 minutes. So okay, so this is our guess. So let's try to translate this statement into equation. And of course, I've been keeping this on the blackboard because I'm using it now. So we consider the action of A lambda on phi. And so we get something, so in the notes, I hope you will get back to it. So we get something multiplied. We get something multiplied by phi. Then we also get something which is unwanted multiplied by omega. So this is an unwanted term. Because if we only have this one, then we do have an eigen, phi is indeed an eigenfunction of operator A lambda. And similarly, we want to look at d phi. Then again, we have the same form of something times phi plus, again, unwanted term. Times omega. Okay? So all this relation can be deriving by, looking at A acting on B lambda, and then you propagate through. So it will be a lateral exercise. Okay. So what do we do? So now we want to basically we want something like this. All right. Then we are home. We don't have any, all the unwanted term dies when we sum them together. Okay? So let me write out what this guy would be. Here you see something kind of rather magical. I guess I call this guy capital lambda lambda. So the capital lambda is actually a function of all the individual spectral parameters. And this guy, so we assume all these two unwanted term dies. It then cancels between the A and D's. Then we are left with this at this. And this guy actually looks like So that's the if the unwanted term cancel each other, this is the eigenvalue you're going to end it up for this particular eigenstate phi. Looks nice, but there's one issue, which is that, well, so lambda, so this expression actually has a pole precisely at the lambda equal to lambda k. But this cannot happen because we know a plus d is actually a trace of ta lambda, which this guy was a polynomial. So this guy should actually be smooth. So there shouldn't be any pole. In other words, there shouldn't be any poles in this function lambda. So that's basically telling you that the residual of lambda equal lambda k of lambda has to equal to 0. Or basically, this equation has to be satisfied. And this is the famous Besser answer equation. And of course, and what miraculously you actually see is that this equation, so in the notes I actually write out what the unwanted terms are. This equation is precisely, if you multiply this to this, this to this, it's precisely the sum of the coefficient of this plus this. So in other words, that once the Besser-Ansatz equation is also the necessary and sufficient conditions for the unwanted term to die off. And therefore, we have the phi indeed become the eigenfunctions of the operator f lambda. So basically the task of solving, basically finding the eigenstate for your spin chain system boils down to find out the solution to this Besser-Ansatz equation and what the appropriate lambda j and lambda k's actually are. And there are many ways to actually solve this equation. I mean, for example, I don't have time to talk about, unfortunately, but now you can actually go off and read, for example, like the case when n actually become very, very large, then there's actually something called a thermodynamical Besser-Ansatz equation, where when all this lambda, all this spectral parameter, or sometimes you call the Besser roots. So this equation was, I think, found by Besser in 1933. So Besser roots actually condenses into a complex plane, and then the whole problem can be translated into something called Riemann-Hilbert problem. So that's where all the kind of fun starts. So this is the main equation I want to get at. So once you have this solution, okay. So basically, so the message is that once you have the solution to the Besser-Ansatz equation, you will plug in. You can find out. You can plug in those lambda k into the eigenfunctions, and of course we know this guy should correspond to basically expansion of q n lambda n. And then you can match the coefficient term by term to work out what's the value of individual conserved charges associated with those eigenstates, well, this particular eigenstate phi. That's all I want to say. Okay, so there's another, a final word, I guess, before we call this a day, is that there's actually a very physical interpretation of what's this happening. I mean, I don't have time to talk about it, but let me just try to refer you to the notes that I think later when I talk about energy and momentum, they can show quite explicitly that by using a definition of a momentum operator I talked about earlier, that the momentum eigenvalue for individual excitation is precisely given by this expression as a function of lambda. So what's on the left-hand side of a Bese-Einstein equation is really something like this. All right? So what's the physical picture? It's really that, as I was trying to tell you earlier, so what's really happening is that individual B lambda are introduced. So for example, for each of B lambda 1, B lambda 2, and so on, there will be a momentum associated, or basically, sorry, I should say that each of B lambda 1, B lambda 2 are really like creation operators for holes or magnons, depends on the sign convention you are using for your energy. And for each of those holes and magnons, they will carry a momentum P lambda given by this. So what it actually does, what Bese-Einstein equation actually tells you is that today you excited one magnon carries the momentum P lambda and drag it across the entire spin chain. So what does it do? Well, it actually just is scattered, of course, with other magnons in your spin chain, well, inside your chain of length n. And while it's scattering pairwise, okay, while it's scattering pairwise, there will be, of course, a scattering matrix describing this physical process, and hence introduce a phase shift to the magnon wave function. All this phase shift are given by this individual, product we are writing down here. So this is actually the scattering matrices between the magnon carries the spectral parameter lambda j and lambda k, or momentum pj and pk. And you multiply it together. That's going to equal to the total phase shift as you kind of propagate your single magnon through it. That's the physical interpretation. So, of course, you can, if you have been smarter, there are another way to actually construct this Bese-Einstein equation. I mean, I was trying to convey in the kind of final parts of notes is that what's really happening is that, if you have this one magnon scattered with many other magnons, generally you have a sort of many-body scattering process. But the beauty of this integrable system, or basically, I was trying to demonstrate this Yang-Baxter equation just now, was that those many-body scattering process can actually be factorized into pairwise, two magnon scattering. Then all you have to do to construct a multi-body scattering matrix is simply multiply them together, which is what we are doing. Right? We are just multiplying all the pairwise scattering process here, and that gives you a total phase shift. And there are, of course, other spectrum. There are other particles that are not just simple magnon, but they could be bound states in the spectrum, which are the poles in those scattering matrices. I mean, those are discussed in my notes also. But I think that's enough for this morning. So hopefully that you will be able to, some of you will go home and try to work through those notes, because actually I would say the excited spin chain play an extremely and in fact recurring roles in the kind of theoretical high-energy physics over the past 20 years actually. And I don't have time, for example, a lot of interesting topics. Things like the spectral curve associated with a lax pair for those spin chain. In fact, they are identified with something called Seibel-Witten curve in the four-dimensional n equals to gate theory. And but moreover, this set of equation also appear in the variety of contexts. For example, finding the vacua of the supersymmetric gate theory, but also finding the scaling dimension of various kinds of operators in the four-dimensional n equals 4 super Young mills when you trying to work on something called ADS-CFT correspondence. So it's actually one of the very important toy models, and surprisingly, like it was found in 1933, and 80 years later, it still play a rather important fundamental role in active research. So that's why I wanted to bring this to you. Okay, so I end